Every day, modern applications push terabytes of data through APIs. Most of these systems run on HTTP, the backbone of the internet. But HTTP was not originally built for complex data pipelines. When the protocol was drafted in 1989, its singular purpose was fetching static text resources to render early web pages. To accomplish this, the engineers created the GET method. It was designed to retrieve a specific document using a simple, concise identifier, the URI string. Today's architectural requirements are entirely different. Modern applications require dense, structured request bodies, like GraphQL queries or deeply nested JSON filter objects, to isolate specific datasets. These payloads clash with the fetch mechanisms HTTP was built to support. Because the protocol was strictly optimized for document retrieval, executing complex queries today requires developers to repurpose existing methods, creating a persistent tension between the data these apps need and the way the network is built to move it. This matrix illustrates the structural gap in HTTP methods. On the x-axis, we have the network guarantee, operations that are safe and idempotent versus operations that change server state. On the y-axis, we have the payload location, data in the URI versus data in a request body. The GET method maps exactly here. It guarantees a safe, idempotent retrieval, but is mechanically restricted to carrying its payload strictly in the URI. The POST method handles the opposite requirement. It readily accepts complex, massive request bodies, but it explicitly lacks any guarantees of safety or idempotency. This empty space represents the exact requirement of modern data APIs. The industry requires a dense body payload while retaining strict safety guarantees. To resolve this, RFC 10008 introduces a new HTTP method, query. Query provides a structural patch to the web's routing infrastructure. It gives engineers the payload capacity of POST, paired precisely with the infrastructural safety of GET. When developers try to force complex data queries through a GET request, the infrastructure breaks down. While the specification recommends supporting at least 8,000 octets, uncoordinated proxies and web servers impose arbitrary size limits on the URI, causing large requests to fail unexpectedly. To even attempt this, structured data must undergo percent encoding. Converting nested JSON objects into a valid URI string introduces massive overhead and inefficient data bloat. There is also a severe security penalty. Because GET parameters live inside DURI, every proxy and server automatically captures those sensitive search filters in plain text within their access logs. At the architectural level, stuffing complex logic into the URI casts every possible combination of search inputs as a distinct REST resource. Routing data queries through GET forces large payloads into the network's control plane. This breaks scalability, it compromises security, and violates basic RESTful design. Recognizing these limitations, the industry adopted a standard workaround, abandoning GET entirely and using POST to pass complex search parameters and GraphQL operations directly in the request body. To understand why this fails at the network level, we have to look at the IETF definitions of safe and idempotent. A safe request guarantees it will not alter server state. An idempotent request guarantees it can be safely repeated without creating duplicate effects after a failure. POST explicitly lacks both of these guarantees. This creates an immediate ambiguity problem for network intermediaries like CDNs and load balancers. A CDN processing a POST request must assume it modifies state, like a payment. Therefore, it actively refuses to cache the result, forcing an expensive round trip. Furthermore, if a connection drops, clients cannot safely retry without risking a duplicate state change. By using a state-changing method for a payload constraint, engineers inadvertently strip away the infrastructure's optimization tools, creating invisible performance bottlenecks at scale. This side-by-side comparison shows a raw HTTP request utilizing the standard workaround on the left and the new RFC 10008 method on the right. The target URI, content type, and body payloads are virtually identical. By changing a single word to query, the ambiguity is eliminated. That method acts as a definitive semantic flag to the entire network stack. When this request hits a CDN, the intermediary recognizes the operation is guaranteed to be safe and idempotent. The CDN can store the response in cache, and the client can automatically retry if the connection times out. Query executes the exact payload logic of a post search, but explicitly bakes the network guarantees directly into the method itself. Caching a request that contains a body payload introduces significant technical complexity to the network layer. To generate a cache key for a query, the cache normalizes the request body, stripping out semantically insignificant encoding differences. It then combines that normalized body with the URI and metadata to calculate a unique hash. This process creates what the RFC calls an equivalent resource. The server generates a conceptual resource representing the exact mathematical combination of the query content and the target. Servers can leverage this by responding to a query indirectly. Using a 303 see other response, the server provides a location header that points the client to a temporary URI containing the query results. The RFC rules regarding redirects are strict here. While most 300-level redirects force the client to maintain the original query method, the 303 redirect explicitly instructs the client to convert its follow-up request into a highly efficient GET. This mechanism allows query to act as a bridge, safely processing heavy data payloads before seamlessly handing the client back to traditional GET-based RESTful retrieval. Implementing query introduces strict new rules for content negotiation. This ensures backend servers process complex inputs without dangerous guesswork. The specification enforces a mandatory content type header. If a query request is missing this header, or if the type contradicts the actual body content, servers must instantly reject it with a 400 bad request. Content sniffing is entirely eliminated. This code shows the accept query response header. It allows a server to proactively inform clients exactly which query formats, like SQL or GraphQL, are supported on that endpoint, utilizing standard structured field syntax. For browser implementation, query is not a core safe-listed method. Any cross-origin request using query will strictly require a pre-flight options request before the browser transmits the payload. Backend engineers and system architects should review RFC 10008 directly and begin evaluating transition paths for their legacy search endpoints. With the formal standardization of the query method, the IETF has aligned the HTTP protocol with the requirements of modern data APIs, providing a native solution for the complex queries that have long strained the web's original design.